Good. So,
Good morning.
okay. And let's take a look at the syllabus. And let's share the screen as well. Today is Wednesday. And okay, do we need more time for lab 4, by the way?
Yes.
Yeah.
Okay.
Yes.
Okay, let's make it do it on Monday. Lab 4, do. And I'll change there in Canvas. And here you go. Okay, so we are writing here the 29th of April. We're going to continue on electromagnetic waves, first hour, and then we do the lab 5, which is 2 resistors. And it's very important that you do all the plotting, right? All the graphing while we are reproducing it here, right? So you don't get confused when you try to work on your own later on. And let's take a look. Let's see, the exam is going to be how many weeks? 1, 2, 3 weeks from now. 3 weeks from now, 22. Okay, so let's take a look here. Yeah, 2021, 22, and we are in chapter 24. Okay, let's see how far we can cover that. And here we go. Here we go. Lab 4 to May 3rd, 3, okay, 26, right? It will be a Monday. No, 4. Monday. Monday is the 4th. Which not the 30. Yeah, lab 4 do. And I will update there in. Oh, Jesus Christ. Let me stop sharing the screen here momentarily. Okay, what was that? Assignments. Okay. That's lab 4 due May 4th, Monday. Let me share the screen now. Save. Here you go. Here is the scenes, right? That the dates, that everything else is due. Okay. Now lab 4 is May 4th. May 4th. Okay. And lab 4. So I logged the homework grades in Canvas. Okay, take a look. The homework grades in Canvas. Take a look at your grades there. Look at your grades and let me know if there's any problem, and let me know if there is any problem, if you have any questions. If you have any questions. The, those are the sections of chapter 24. We covered the nature of the electromagnetic waves. It's a combination of electric and magnetic fields that change in time. Nature of E&M waves. E&M waves. It is a combination of electric and magnetic fields that vary in time. The most let's say, important E&M wave is the one in which the electric and magnetic fields vary in time as a sinusoidal wave. Okay, that's so it would be something like the following. Because it's a wave, it follows that same type of equation that you saw before in waves, right? So here you go. You have the amplitude of the wave, and can be either a sine or a cosine. Okay, so here you go. Since it will vary in time, we will have omega t term right in here, but there is more because it's a wave, right? There must have a kx minus omega t term inside here, the sign. And this k, what this k is? This k is 2 pi over lambda. Like that, 2 pi over lambda. And this omega t, what is this omega t? This omega t is the angular frequency. 2 pi times the frequency. 2 pi times the frequency, like that. We usually write this term as k and this one here as omega. And another way of expressing this equation. Okay, oops, undo it. Another way of expressing this equation would be to put this term, the K term, in evidence. And when we put the K term in evidence, we have to multiply by lambda and divide by 2 pi, like that. Okay, what happens to the 2 pi here? Those 2 pi, they cancel out, right? And 2 pi cancels out. We're left with lambda f. And lambda f is what? Is the velocity of the wave. The velocity of the wave, right? Remember that? That's the equation of a plane wave. We call it the sine wave is called a planar wave. Okay, this is the expression of a planar wave. When it comes to the magnetic field, we have something very similar. Okay, and you saw the simulation too, right? B, I mean B naught, and that's a forward propagating wave. The minus sign in the equation states that the wave is a forward propagating wave. This minus sign right in here. What else do we have to know? Okay, the electric and magnetic fields are perpendicular to each other. Okay, but again, you're gonna find some exceptions out there in the world. Okay, but for propagation in the vacuum, okay, for propagation in the vacuum, the electric and magnetic fields are perpendicular to each other. Later on, if you get into the thing, you're going to see that it's not exactly like that, but that's okay to believe that now. Okay, so here you go, x minus vt. See that? X minus vt here. It's not difficult to memorize that stuff, right? So the argument of the sine or the argument of the cosine must be unitless. So what we have here, you have meter and you have meter. So meter cancel with meter. And now we're left with the radian. Okay? Can you remember that easily? Okay, here you go. I'm gonna write that in terms of kx, right? I think this format here is more intuitive. It's more intuitive because of this term x minus vt. I'm gonna put k here as well. The wave k is the wave number. K. For the B field, we have a similar. For the B field, we have a similar expression. Okay. In the above, K is called the wave number. Perpendicular to each other. So here we go. How are we going to express that, right? Here we go. So in order to be perpendicular to each other, I'm going to copy those two. We can express that in vectorial terms. Okay. So let's say this one is in the X direction. Okay. And this one here is in the, it must be either in the Z direction or in the Y direction. Let me put it in the Y direction. Here you go. Right? That and you saw the simulation, right? How it ended. Let's take a look at that link. And let's see here. Ended. Okay, so let's see if we have another one. Oops, nope. Two results. Okay, that's the one I want. Oops, didn't copy. Let's go back. Copy. Yeah, okay, here you go. That's how that wave looks like. The electric field changes in a sinusoidal fashion, and it's moving the forward direction. In this case, he got let's see. No, wait a minute. Okay, he got the electric field in the Y direction, and he got the magnetic field in the Z direction. That's how he did it in this specific case. But that's how it looks like. You know, the electric field perpendicular to the magnetic field. Let's make it consistent with this drawing, right? Here you go. So snipping tool. Okay, so here you go. The magnetic field, he made it along the Z direction. I'm going to replace here. And the electric field, he put it along the Y direction. The Y direction. If you do the if you use the right hand ruler, moving from the palm of your hand, moving from the E field to the B field, comma, you get the direction of propagation of the electromagnetic wave. In this case, along the x direction. Okay, along the x direction. Along the x direction. And that's what this wave is moving, right? Moving along the positive x direction. Okay, and we talked about the electromagnetic spectrum. We talked about the electromagnetic spectrum as well. Magnetic spectrum as well. The type as well. Here we go. The type of electromagnetic wave depends on the wavelengths of the wave. Okay? From radio waves through microwave, across the infrared spectrum, the visible, let's see, radio waves, the wave of the wave from long wavelengths to short wavelengths. We have radio waves, microwaves, infrared, visible radiation, visible light, the one that we are sensitive to. Our eyes are sensitive to visible light. Everything else you have, you need a detector. Visible light, we have ultraviolet, X-rays, and finally, gamma rays. Those are the electromagnetic spectrum. The shorter the wavelengths, the more energy the electromagnetic wave has. Okay? That's why we have to protect ourselves against those three types of electromagnetic waves: gamma rays, X-rays, and ultraviolet. Okay, we talked about the speed of the light. Nature of the electromagnetic spectrum. Okay. Energy carried by the speed of the light, 300,000 kilometers per second, right? Speed of the light in the vacuum is 300,000 kilometers per second. In other media, this speed is lower. And we are going to see later on how low the speed is. The speed is lower. Now let's talk about the energy carried by the electromagnetic wave. Remember that the electric and magnetic fields have energy. Okay, has energy. The electric and magnetic fields have energy associated with them. Consequently, an electromagnetic wave must also have energy associated with it. And we saw that the energy density there's an equation for the energy per unit of volume, right? Oh, we already know that both electric and magnetic fields carry energy within them. We even derived the equations for the energy density. Do you remember that? It's not difficult to memorize. The amount of energy per unit of volume for any electric field is given by this expression. And the amount of energy per unit of volume for the magnetic field for any wave is this one right in here. It's given by this relation right in here. Since an electromagnetic wave, since an electromagnetic wave is made up of electric and magnetic fields, right? The net energy density will be the summation of these two separate expressions. And I'm going to denote that by the letter U. U sub E plus U sub B. U right in here. U sub E is this one here. And we have this simpler expression. Doesn't get any simpler than that, right? We're going to put the half in evidence. Like that. Okay. Okay, and there is a very important relation that you must memorize. We cannot derive it here, but there is a very important relation for an electromagnetic wave that you must memorize, okay? And what is the relation? Okay, it happens that for an electromagnetic wave, the energy density in the electric field ends up being equal to the energy density in the magnetic field. Okay, and so if it's, because of this equality, right? We have this relation right in here. Energy density in the electric field equal to the energy density in the magnetic field. Put here an equal sign like that. We can get, by the way, yeah, okay. Keep this way. The half sign cancels out. The half factor, right? Not sign, the half factor cancels out. And we can have an expression between the electric and magnetic fields. Okay, and here go. If we solve for the electric field first, we get something like that. Like that. And which, by the way, is c squared, right? Epsilon naught, mu naught. Oh, sorry, it should be upstairs. Should be upstairs, not downstairs. Is the inverse of it, like that. Another student coming in. And we can here write that. E equal to CB. And also we have this other relationship here. And when I'm talking about E, I'm talking about the E that's a function of time, right? E and B that's a function of time. Here's another way of expressing it. And now I can substitute this relationship that we got right in here. B is going to be square. Like that. And I'm going to, it's better if you put this square right in here, right? No, let's leave here. Well, you know what? I'm going to take this dependence on t here. Otherwise, the notation becomes too confusing, right? That's, but it's implicit, stay implicit that E is a function of time. C square and now we can put E in evidence, E squared in evidence. Like that. Can we do better than that? Well, remember that 1 divided by c squared is epsilon naught, mu naught. So we can, 1 divided by c, let me write that down separately here. C squared is 1 over mu naught epsilon naught like that. So when I replace C right here in this equation, I get something like that. And the energy density becomes easier. Epsilon naught E squared. Like that. And the energy density is a function of time, right? Because the electric field also is a function of time. And because the electric field is a function of time, because the electric field is a function of time in terms of, don't forget, in terms of sine and cosine, right? In terms of the trigonometric function, comma, we can define the root mean square value of the electric field, just like we did for AC circuits. Or root mean square value, right, is the amplitude divided by the square root of 2. Don't forget, this one here is the amplitude. That's why I put E naught here. That's why I put E naught. And we have 1 divided by square root, right? And now we can also have the root mean square value of the energy density, something that is a constant, right? Like that. Let's see here. I don't want that. I want the other one. This one here. Root mean square and root mean square value. The root mean square value is the E naught, raised to the square, E naught, E naught square root. Like that. Like that. E naught is squared. And that's 2 divided by 2. And we can also here write that in terms of the B field. Right? So here we go. We have the relationship between E and B. Okay, right in here. Why is it doing that? Let's put that here first. Didn't copy it. Let's copy it again. Here you go. I want to copy this one here. Okay, what? It's not copying for some reason. Let's try it again. A third time. Let's try the third time. What's going on here? E. I want this one here. Yeah, here you go. Now we have it right. And let's put the not. Yeah, like that. Oh, let's not. Okay. And then can we simplify further? We can. We can simplify it further, right? Just to write the c squared in terms of mu naught and epsilon naught. And we're going to cancel out this epsilon naught. Mu naught and epsilon naught. And this c disappears, right? And the epsilon naught cancels out. I'm going to write that down with the half separated from this value, okay? Even better, I'm going to put the mu naught downstairs and put this one side by side with the other. Next, let's see, not side by side, one just below the other, right? Let's write down the half right here. And we can eliminate this half. Okay, we have a half term here for the electric field. We have a half term here for the magnetic field. We have a epsilon naught term here for the electric field, and we have a 1 divided by mu naught for the magnetic field. Then you have the field, the amplitude of the field square, the amplitude of the field square. That's not difficult to memorize, right? So far for the so we are done with this chapter 24. Here you go. We had lab 1 and 2 in the first exam, right? Let's take a look at the syllabus. Syllabus right here. So sorry, we had lab 1 and 2 for the second exam. So far, we are going to have lab 3 for the second exam and lab 4 as well. Okay, so for now, energy carried by electromagnetic wave, we did that. We're going to skip this chapter. We're going to skip polarization, okay, for now. Skip for now. Let's put like skip for now. Let's see, we're skipping this one as well. Skip. Don't forget, we had that 20.5 was the beginning of our alternating circuit, right? He covered before in chapter 20. I prefer to cover it on chapter 23 because we need to know about the generator, how we create an AC source. The generator is an AC source. And that was seen only in chapter 22, right? Yeah, 22. Electric generator right in here. You need this electric generator before we start talking about AC circuits, because the electric generator is the source of AC circuit. So it's part of chapter 20, 20.5. Capacitors and capacitive reactance, inductive reactance, AC circuits containing resistance, capacitance, and inductance. We covered that, all of that. And so far, we have labs 3 and 4. Okay. Any questions? Let's see if you have any questions. Jeremy's trying to come in. And let's take a look at the book. Right? What does he cover there in the book for? Lunch? Lunch. Okay, nature of the electromagnetic wave. You need to generate an electromagnetic wave, you need a circuit. You need an AC circuit. And that's exactly what you have here. This AC circuit is like an antenna. You know, get two pieces of wire connected to your AC, and you don't have to close the loop, okay? You don't have to get a metal, one conducting rod, stick it at one end of your AC source. It's just like get a wire, plug it into the one polarity of your wall outlet, and get a second wire, plug it in the other hole of the wall outlet. You're going to create an antenna, an electromagnetic antenna. At a given instant of time, it's going to become, neutrally charged. Then as time goes by, it becomes positively and negatively charged, okay? The ends. And this thing is going to flip back and forth, back and forth, back and forth. And, at this point in time, the intensity of the wave is zero, at time t equal to zero. 1/4 of a wave, 1/4 of a period of the wave. You have maximum amplitude in the negative direction, okay? And then later on, when it's neutrally, no charges, right? At the end, goes back to zero. And when it inverts the polarity, it has maximum amplitude in the positive direction. That's how you should visualize it. Okay, and finally, we have this full wave. Okay, that's a very good illustration for what you see here is an electric dipole. What you see right in here is an electric dipole. And here is the electric field. Okay, he's not drawing the magnetic field. In each part of the drawing, the red arrow. Okay, the red arrow, that's the red arrow that he's referring to. Represent the electric field produced at the point P by the oscillating charges on the antenna at the indicated time. The black arrows represent the electric fields created at earlier times. For simplicity, only the fields propagated to the right are shown. He didn't illustrate the magnetic field, okay? But you can picture the magnetic field as being in this plane here, perpendicular, coming out of the board. Let's see if I have a drawing about that too. See, illustrations. electromagnetic induction, electromagnetic wave, right in here. Okay, so he go magnetic field, he go electric field. Note, see that the electric field is perpendicular to the magnetic field, right? And he go variable magnetic field. Okay, here you go. Here's my transmitting antenna. Very similar to the drawing that I believe I showed that to you, right? Here you go. As time goes by, charges build up. Very similar to the drawing that the book showed. I just didn't put the electromagnetic wave there. Okay, I'm showing you how the generator, right? The charges in the generator changes as time goes by. Okay, and that's the electric dipole antenna. And that's the magnetic dipole antenna. Okay. Both of them generate electromagnetic waves. Both of them generate electromagnetic waves. At a given instant of time, let's say the magnetic field is 0, right? But as time goes by, the field starts building up and propagating to the right. Okay, this is showing that the magnetic field here is more intense than here. But because the magnetic field is changing it with time, it is also inducing an electric field. The electric field is circulating around each of those magnetic fields. Okay? But in this region, they cancel out because they have the same amplitude, but opposite direction. And what is left is an electric field downwards, an electric field that's downwards and perpendicular to the magnetic fields. Here we have the same thing, another electric field down. One downward, the other upwards, right? And here you go, this one cancels a little bit with this other one, this one cancels a little bit with the other one, and so on, right? And then we end up getting this electric field. Okay? That's the story behind the electromagnetic wave. Go. That's another way of generating an electromagnetic wave. Okay, with a magnetic field. And here you go. Exactly what you saw in the illustration. Okay, in reality, okay, this is not a different way. This is the same. This is still a electric dipole antenna, okay? Here he is illustrating the fact that the magnetic field lies in this direction, perpendicular to the electric field. Perpendicular to the electric field, right here. And here you go, the electric dipole antenna, electric and magnetic fields are perpendicular to each other. Here we have a LC circuit that can generate this type of wave. He took away the resistance. He didn't put the resistance there, okay? An antenna, 2 wires connected to an LC circuit generates this bouncing back and forth of the electric charge. And That's the electromagnetic spectrum that I mentioned to you. Radio wave, microwaves. Within the radio waves, we have AM and FM waves. Memorize this spectrum, right? Here is the region where the human eye is sensitive, the visible spectrum. The story behind the discovery of the electromagnetic spectrum is fantastic, okay? It's just very interesting. The first invisible electromagnetic wave that we discovered was the infrared wave. That was the first invisible one. And then as time went by, we discovered radio waves as well, X-rays, gamma rays, ultraviolet. Okay. Okay. Pulse oximetry, the amount of oxygen. Oh, that's a very important device, okay? They were using this device during the COVID pandemic. At the beginning, they didn't understand much the pandemic, right? But they eventually figured out that all they have to do to save people was to measure the oxygen in the amount of oxygen carried in the blood. And we have this simple device that can do that. Okay, a non-invasive device that's used to measure called the pulse oximeter. Clips onto a flashy semi-transparent part of the body with your fingertip. The clip uses light-emitting diodes to pass light of two wavelengths. This one is 660, that's a red, and this one is 940 nanometers. 660 nanometers, 940 nanometers, red and infrared. Through the blood, carrying tissue, and monitors how much light of each wavelength gets absorbed on the way through. Since oxygenated and deoxygenated hemoglobin absorb light of those wavelengths differently, the percentage of oxygenated hemoglobin can be determined. Okay, it's just a very simple device that shine red lights through your finger and shine infrared lights through your finger. And oxygenated hemoglobin and deoxygenated hemoglobin absorb light of those two wavelengths differently. So just by measuring the intensity of those two lights after the finger, we can determine if the blood is oxygenated or not. Okay? So below 90% is considered to be low and is called hypoxemia, and below 80% may result in organ failure. Okay. So the value of should be oxygenated hemoglobin should be between 95% and 100%. Okay, so that's the device. That's how it works. But he's not asking about the device. He's asking what are the frequencies of light emitted by the LEDs. Those LEDs are very cheap, by the way. Okay, you can buy those things very easily. 10 cents. You can buy on. Those are mass manufactured devices. It's just like going to the supermarket and buy, a grain of rice. Huh? Those LEDs are all about. And what are the frequencies of light emitted by the LEDs? You have the wavelengths, and you have the speed of the light, right? You can come up with, let me just, I'm gonna do like that, example, right? Example. Light of wavelengths as 606 nanometers, okay? Which is the same as 6.6 times 10 to minus 7 meters. Nanometers 10 to minus 9 times 100, right? You get something like that. Light off of wavelength, 606 nanometer, and 900, let's see, 940, and 940 nanometers. Let light, of wavelengths. What is their frequency? Example A. Okay, what's the next? B. In what regions of the electromagnetic spectrum do the two frequencies fall? Already told you, right? This one is in the red, this one is the infrared. Can one see with the naked eye both types of light being emitted by the device? Okay. In the case of the red, yeah, you will be able to see it. And what about A, B? Only two. Okay, here you go. Here's the equation, right? C, the velocity of the wave is the frequency times the wavelengths. You do the math, you get that that frequency. Okay, and referring to false indivisible. See that? False indivisible. You have, in order to answer this question, B1, which frequency of the spectrum does it fall? You have to look at figure 24.9, the electromagnetic spectrum. You have to look at this one. Okay. The electromagnetic spectrum. And it has all the values, numerical values for the wavelengths and the frequency. Okay, and pulse oximetry. That's the device. Very simple device, by the way. And the other is the infrared. What time is that? We are almost getting to our break. Let's see if I have anything else to cover. Speed of light, right? Here you go. That's how they measure that's one way to measure the speed of the light. I'm not gonna cover that. And 300,000 kilometers per second. Energy carried by electromagnetic waves. We work that out. Okay. And average energy density, the root mean square. Okay, and there is one more thing that I have to mention is the Poynting vector. The Poynting vector is an important vector that measures the total energy per unit of area per unit of time that's incident in a surface. Okay, and that's the only thing that I didn't cover, okay? 16.8, okay. Okay, so P, okay, so here you go. And let light, what's their frequency? Here you go, I'm gonna put here, use the relation lambda F equal to C, right? Lambda symbol. Lambda F equal to C. These wavelengths and so for F. These wavelengths correspond to the red light and input red light and infrared light. comfortable. So we have now this definition. And let's, did I write that down? The direction, let's not forget the direction of propagation of a wave is of the electromagnetic wave. Electromagnetic wave is given by the right-hand rule. Okay, curl the palm of your hand from the electric field towards the magnetic field, and your thumb points in the direction the wave is propagating. Okay, which is the direction of the pointing vector. Okay, and how is the pointing vector defined, right? Pointing vector is defined as the power of the wave, pointing vector S divided by the area that is an electromagnetic wave is incident. Okay, and let's not forget that the power is what? Is delta U divided by delta T. Okay, and I'm going to put the delta T downstairs. Delta T downstairs. And I'm going to do something else too. I'm going to multiply the top by C and the bottom by C as well. Oh, by C as well. Okay. And when we do that, C delta T, oops. C delta T can be written down as delta X, the amount that the wave moved in a delta T time, right? Okay, okay, so here you go. There's one more thing. What you have here, notice that this area that the electromagnetic wave is incident times this delta X is going to be the volume, delta V, that the wave fills. Okay, so I'm going to put it lowercase v. Delta V here in this case stands for volume. Delta V in the above. Oh, gosh, forget that. Let's see, in the above, delta V is the volume of the wave fills. Okay? Consequently, delta E over delta V, consequently, we have that delta U over delta V is going to be equal to the energy density of the wave. Okay? And now we can here write it. Lowercase u, right? Cu, which, by the way, is related to the electric field as well. We saw that U is epsilon naught times E squared. Epsilon naught times E squared. And this is a function of time. We have a C here. We can here write that the C is 1 divided by the square root. Now the square root, let's see. Let's put let's get this one here. 1 divided by epsilon naught mu naught. Epsilon naught mu naught. And we end up with square root here. Let's see how I'm gonna do it. I'm gonna do this way. Yeah, here you go. Like that. Yeah. Epsilon naught over mu naught is square root. In terms of the magnetic field, okay, it's that's one way, right? That's one way. And you can either write this way or this way, whatever you prefer, right? So for the magnetic field, I'm going to just give you the final answer. And it is given by something like that. HC over mu naught B squared. Okay, we are almost. And don't forget, that's the Poynting vector. That's the power per unit of area, okay? The Poynting vector represents the power per unit area of a given electromagnetic wave. Magnetic wave, okay? And that's the expression that we have for both the electric and magnetic field. Then you can also do that for the root mean square value, right? And that's the derivation, the same derivation that we did. Okay, he did it slightly different from me, but the final results are the same. Okay, and this one we are not covering. Okay, we're not covering this one. So what time is that? It is 10:57. Let's take our break and break 10:57 a.m. Okay, let's see here. 55, that should be 11:12 a.m., right? Yeah, 11:12 a.m. So if you don't have any questions, I see you in 15 minutes. Oh, someone asked the question. Let's see, Professor, I have a question for lab 4. I noticed that some of the columns have negative numbers. How do we find the sig figs? Okay. Is Susan still there? Hi, Susan. Okay, good. Let's talk about that after the break, okay? The significant figures is the same, okay? You treat the negative numbers as though as they are positive in the table. So, okay, that's straightforward, okay? I will share my screen. Go. Lab number 5, right? Let's do lab number 5 now. I'll break number 5.
Professor,
Yeah,
my question is, we have 5 labs. I thought it was 4 labs.
that's right. We have done 4 labs as of now. We're going to do lab number 5 today.
Okay, so in total we have 5. Okay.
Okay.
All right.
I'm looking for my notes of lab number 5, and just bear with me a few minutes. Okay, lab. Let's try it here. Lab 5. Okay. Here you go. I got it. Here you go. Lab 5. Circuit resistor resistors. And look what we're doing, right? In lab 4. In lab 4, the experiment consisted of very fine Ohm's law with a single resistor in the circuit. Okay? In this lab, we will do the same for two resistors in series. Okay? In lab 6, we will repeat this for two resistors in parallel. Okay, so let me upload the spreadsheets for this lab, raw data. Let's see here. The busy. Activity. Easy. Save. Wait. Each. Let me first check if everything is fine with your spreadsheets. Let's see here. It's good. That looks good. View. Let me. That looks good. Mm. Mm. Pause the record momentarily and remind me to turn on the recording again, okay? Resume recording, and I'm gonna share my screen, right? And I'm gonna go to that very same site that we used before, okay? Site of the University of Colorado. PET. Okay, let's look at here. PET. PET. PET simulations, Colorado. That's the one I want. And we want the physics simulations. And next one, I want the electricity. Okay, and circuit, that's AC. I don't want the AC. I want the DC now. Virtual lab, circuit construction kit. Let's see here. Let's try this one. This one here. Let's see this one. Introduction. Let's see if that one. Okay, so looks like we have it. We have yeah, we do have the multimeter and the ammeter here. And here is my roster. Let me share. Insert. Let's open our one of the spreadsheets. See here. Each one is the lucky one. Well, let's get it 15, group 15, right? Here the spreadsheet that you should look at. Okay, and how this experiment is performed. Okay, so first let's start with the materials, right? Notice that we have two resistors, R1 and R2, right? So definitely we are going to need two resistors, resistor 1 and resistor 2. Resistor 1 and 2. And I'm gonna go to the the simulation here, I'm gonna get two resistors. Let's see, I want two different resistors. One, let's see, this one that has 10 ohms, right? And let me get this one, let's put it 20 ohms. Whatever, 31 ohms. Okay, digital multimeter. Okay, the digital multimeter is a voltmeter and an ammeter. A power supply. Okay, we have been using power supply since the very first experiment. The only experiment that we didn't use a power supply was when we were making just measurements of the resistance. Okay, power supply. The power supply in my simulation is the battery. Two red banana cables, two alligator clips. The simulations don't show banana cables and the alligator clips, okay? We're going to need a prototype board as well, just like we used before in lab number 3. And two black banana cables. Okay. The first step in the procedure is to measure the resistance of each resistor using the DMM. That's where we get the values here, R1 and R2. Okay? R1 and R2. Okay, we're going to turn on the power supply, adjust the power supply to 10 volts. And that's what we're going to do with our battery here. Let's put it at 10 volts. Here you go. Our battery is 10 volts now. And let's see if I can get my slides as well. Lab slides. Two resistors. Yeah, that's the one. Okay. Red banana cable, plug it to the red jack. Okay, in the simulation, you cannot measure in the FET simulation, you cannot measure the resistance of the resistors. They don't have an ohmmeter here. They have only a voltmeter and an ammeter. Okay, so but that's how you measure, right? R1 and R2. You adjust the DMM to measure resistance, and we start by putting the circuit together. Okay, the red banana cable goes into the red jack of the power supply. Connect the other end of the red banana cable to one of the leads of the resistor. So it is going to look like that. Here you go. Power supply, right? Here's the symbol of the power supply. Red banana cable. This arrow here means alligator clip. Clips into one end of the resistor. And that's what I'm going to do in this simulation as well. Here you go. Wire. That should be my red banana cable. And by the way, I'm gonna add a switch in there. so we can control the circuit. Here's my wire. And here we go. And the other wire connected to the resistor number 2. And we are going to close the circuit. Okay, here you go. Let's see, I want to move a little bit to the left so it looks good, right? And this one here, I want to cut as well. And I want to put a 1, 2, 3, 4. Let's see, 1, 2, 3, 4. 1, 2, 3, 4. That's good. I'm going to put another wire right here. Here. Can I move a little bit more? 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. Yeah, okay, good. And how does it look in my? Gonna look like that. Here you go. Resistor 1, resistor 2. Okay, resistor 1 and resistor 2 are plugged into the breadboard just like that. One resistor here, and they must be in the same row. In the same row. Okay, and then we close the circuit. Just like I have the circuit closed in there. That's the diagram, the schematics. And connect the other end of the red button. Let's see. Connect the resistor 1 and 2 in series using the prototype board. Use the second alligator clip to connect the black cable to the second lead of resistor 2. Connect the other end of the black cable to the negative terminal of the power supply. We close the circuit. Okay, the circuit, once we close the circuit, the circuit is still open. Once we close the circuit, right, the current should be moving through it. Very slow, but it's moving anyway. And I'm going to put the circuit for the current to flow in the conventional case. The current flows in the clockwise direction. The electrons flow in the counterclockwise direction. That's the picture that you have to have in your mind. That's what's happening in the circuit when we close it and put the current to flow. Now we are going to measure the voltage in this circuit. Okay, we are going to measure the total voltage. The total voltage is measured by putting the voltmeter at the ends of the power supply. Okay. And then we are going to measure the voltage across resistor 1. I call this one resistor 1. And we're going to measure the voltage across resistor 2. I call this one resistor 2. Okay? That's what we're going to do. And we are going to take the measurements. Here you go. That's the voltage of the power supply. Here is the That's the voltage that we measure, right? Of the power supply. Here's the voltage across resistor 1. Here's the voltage across resistor 2. This one here. Let's see here. Okay. Okay, here the following. Let me. Here is a measurement. Is a measurement, and this measurement, you have to look at the table for V sub. Okay, table for V sub. And those two are measurements taken with the voltmeter. Those three are measurements taken with the voltmeter. Okay. And this is a measurement taken with the ammeter. Let me write that down for you. So we don't forget, right? Going through it. We will measure, here you go. We will measure the following values. 1, V sub, okay? The voltage indicated in the screen of the power supply, okay? And I want to show you for the significant figures, okay? Very important. Sig figs. See here, it should be here. Yeah, here you go. That's the one. Okay. That first V sub refers to this second table. Okay. Refers to the second table. Second table of P07 sigfig.pdf. Okay. Indicating the screen of the power supply. The sig fig for this value is given in the second table of P07 sigfig.pdf. Second table. V sub. Okay. We're going to measure V sub. We're going to measure the total, the voltage indicated the screen, the voltage indicated in the screen of the DMM. Okay. R, right? R given. R given by now this one is the third table. Third table. The voltage indicated for these values, these values, right? Let's put it. Are given by the third table of P07 sig fig. Third table. 1, 2, 3. Then we have V1 of the DMM. The sig fig for these values are given in the third table again. Yeah, third table as well. And then we have V2, which is again is the voltage across the second resistor. In the third table, okay. The following values. What else are we going to measure? We're going to measure Here you go. The current I. We're gonna measure the current I. The current in the circuit indicated in the screen of the E&M. The sig fig of this. Okay, sig fig 1, 2, 3 is given by the force table. Okay, 4 tables, and for this value given in the force table of P07 sig fig .pdf. Everybody's following? Okay. So the experiment again is going to be done in the following way. Okay. Just repeating what I said, right? Measure the V total with the multimeter. Measure the V1, which is the voltage across the first resistor. Measure V2, which is the voltage across the second resistor. And then, finally, we are going to measure the current flowing through the circuit. Okay? That's what we have here. And what else? What else are we going to do? We're going to vary the voltage of the power supply. Okay? Start with the V sub of 10 volts. We're going to measure this one, V total, V1, and V2. Okay? So, starting with now we'll measure the following values. Starting with V sub equal to 10 volts, comma, we will measure V total. We'll measure V total, V1, and V2. And V2. That's what we do first. Okay, repeat for V sub equal to 8 volts, 8 volts, 6 volts, 4 volts, and 2.8 volts. There's a reason why we use 2.8 instead of 2. Wait a minute. Okay, this one can go to 2. It's not 2.8, it's 2. Okay, this one goes to 2. Okay, and 2. Repeat 11, step 11 for V sub, right? Now 13. So let's take a look at our, here you go. We're not measuring current yet. We're not measuring current yet, okay? So here you go, multimeter. Right, multimeter connected to those 2 terminals of the power supply. This point is exactly the same as this one, and this point is exactly the same as this one, because we have a conductor here. There is no loss of electric potential along the conductor. Conductor is, is a ideal conductor. We invert the polarity, right? And we take the negative values. That's what we're doing here. 10, 8, 6, 4, 3. This one is 3. Let's see here. There is, yeah, it looks like there's a mistake here. Yeah, there is a mistake here in the group 15. Let me see the other spreadsheets. Raw data. Raw data. Let's see this one here, group number 3. Yeah, okay. Okay, but it's not gonna affect your lab, okay? Yeah, there's a mistake here. Definitely there's a mistake here because this V sub here was supposed to be close to this V total here. Okay, but that's not going to affect your graphs. Okay, don't worry about there is a mistake indeed here, but don't worry about those mistakes because it's not going to affect your final result. Okay, and we didn't. So what we have done so far, right? We have measured only the V total. We inverted the polarity. Let me close this one. We inverted the polarity of the power supply. And then we got negative values for the voltage. Okay. Here, then we're doing V1 now, right? So I already showed to you how to do that in the simulation, right? And the simulation looks just like that as well. Just like that. Let's go to the simulation. That's V1. That's V1. Let me move this guy away. Okay. And we are varying, right? The potential of the battery from 10 to 8 of the power supply. From 8 to 6, take a measurement. Take a measurement here. From 6 to 4, take a measurement. And from 4 to 2 point whatever. Okay, from 4 it should be 2.8, 2.9. Okay, and take the voltage measurement. That's exactly what you have right in here. Invert the polarity and repeat the measurements. Okay, and you're going to have those values here. Invert the polarity. Let's see. The polarity is inverted. Let's see here. Oh, right in here. And the voltage is negative. Okay. That's how we do V1. To do V2, plug the voltmeter at the other two ends of the resistor. Oh, and let's not forget, right? Invert the polarity back and start all over again on the other direction. 2.9, 4, take the measurement, 6, 8, 605, and 10. Invert the polarity and repeat the whole measurement. And that's what we did for V1 right in here. Oh, for V2 right in here. Positive and negative. Okay, and this voltmeter. Okay, don't forget the resistors are in this breadboard. Okay, V1, V total that we did, V total, and now we're going to do V2. Here you go. In parallel with the resistor number 2. Going back to the simulation, we're already here, right? We're already here in the simulation. V total from 10 to 2.8, right? And invert the polarity, do the measurement again. 1, 2, 3, 4. Let's now do the measurement of the current. For the current measurement, we have to start from scratch. And let me also document the measuring the voltage of the total. Next. I got a document here in my notes. We'll measure V total, V1 and V2. We start with V total. We start with V total. Mm-hmm. Like that. Change the polarity. It's all documented here. Okay, and next. Okay, here you go. Measuring voltage across resistor 1, V1. Measure voltage for resistor 2, V2. And now we're going to measure the current in the circuit. Measuring current in the circuit. Everything apart, and start from scratch. Okay, everything apart and start from scratch. And that's let's see here, negative. Let's see here, power supply R1. Okay, that's V2. V2. Okay, and now we start from scratch. Connect to the ammeter, positive to the positive of the ammeter. Then the negative is going to go to the resistor. Resistors 1 and 2 in series, and close the circuit. Okay. In this case, I cannot show it how it's done because the ammeter of them is not the realistic one, unfortunately. But suppose that the ammeter works something like that. Okay, and not something like that. Okay, suppose this was an ammeter. I'm going to show to you how we connect the ammeter. The ammeter is connected like that. Okay, that will be the correct way of connecting an ammeter in real life. Okay, the ammeter is in series with the resistors. That's a big difference between the ammeter and the voltmeter. Voltmeter must be connected in parallel, ammeter must be connected in series. Let's write that down. Now, what time is that? Let's see. Wow, 12:02, huh? It's time for our break, huh? Okay, measuring current. Let me just write that down here. Ammeter is connected in series and voltmeter is connected in parallel. Okay. Let me see if there is any questions. No. 12:02 right now. And by connecting in series, here you go. We are connected in series. You change the voltage of the power supply from 10 to 2.8, and then invert the polarity, okay? And you get negative readings. And that's what you have right in here. Positive readings, negative readings, you know? And the same for the voltage, right? They are all measurements. Let me highlight it here. Measurements. What do you have to plot? That's the important part, right? Now that we have all the data, measuring, set up the circuit. So I'm going to measuring the current. So I need you to plot 3 graphs. That's the most important part. Okay. Plot 3 graphs. V total along the y-axis, and I current along the x-axis. Okay, V total. I'm gonna document here what are the cells. Okay, let's see if you have time. I wanna give a break. 12:05. Here we go. V total is J11 through J20. J11 cells J11 to J20, and I cells oops cells here you go G11 to G20 cells G11 to G20. Okay, that's V total. Plot V1. I think I'm gonna finish it. Let's see. Let me give you everything before you go to the break, right? Plot V1. V1 is going to be cells V1 H11 through H20. H11. Okay, I is still G11 to G20, right? And then V2 cells I11, I11 to I20, I20. Oh, here you go. Let's make sure it's I. Yeah, V2 is in I. Good. Those are the three graphs that you have to plot. And now we can have our break. Break 12:06 to 12:21 p.m. 12:06 p.m. Okay, and I see you in 15 minutes. Let's see, Susan, you asked me a question. The first graph. Let's see. Here you go. You want to see the cells? Is that what you want to see? The cells that you have to highlight? Okay. 1, 2, 3. Here you go. J11 to J20. Okay. V total is J11 to J20, right? V1 is H, and V2 is H. The cells for the current doesn't change, remains the same. Okay. So, okay, so now we got 2 more minutes for our break, right? 2 more minutes, no. We start a little bit late for our break, so 12:08 to 12:23, right? I see you in 15 minutes. Stop sharing. Moving back, and we are now going to plot the graphs that you have to plot for this activity, right? Here you go. First graph, V total, I. Okay. When you plot V total I, you should get a straight line according to Ohm's law, with the slope being equal to the sum of those two resistors. Okay? Because the resistors are in series. Here you go. Here's the graph. Okay? Click one of the data points, right click, add trend line, display equation on chart, display R square value on chart. Right? And I have it here. Once you do that, you're gonna get this slope, 19,342, and you are going to log this slope right in here in cell H51. Let's see. What's the 19342? 19342. Copy, copy, copy. It doesn't copy. 19342. Okay. 19342. You can see that we have a very small percentage difference, 0.6% only. Okay. The slope has a unit, and the percentage difference, which is the delta, also has a unit. This is an experiment that works very well. Everybody did that? Make sure you plot the graphs. Let's see here. Okay, Susan got it, right? Anybody else?
Yes.
Kimberly, you got you? Okay. Oni, right? Oni got?
Yes.
Okay, thank you. Now, next one. V1 and I. Yeah. Let's see. So, yes, graph. Okay. Princess, Dana, Ryan. Okay, good. Now, next one is V1 and I. Right? Chart, scatter, plot. Now, we are going to get a straight line too, but now the slope is supposed to be equal to the first resistor, R1. Okay, remember when we are collecting not this one right here, right? When we are collecting our data, right? The voltmeter was in parallel with R1. That's why you're supposed to get the slope equal to R1. When we did for the V total, right? The multimeter was in parallel with the two resistors in series. That's why we're getting a slope equal to R1 plus R2. And let's see, let right click, add trend line, display R square, display equation chart. What are we getting? 11,853. 11,853, okay? And should be, this one here, 11,851. Wow. That's a very small percentage difference. 11,853. V1, 11,853. 0.0169%. And the last graph, V2, control key, right? I, insert, chart, scatter. Click, right click, add trend line, display equation chart, display R square on chart. Here you go, 7367. 7367. 0.04%. Right? Here you go, 7370. That's what we measure for the resistor number 2. Okay. That's 12:31. We have 20 more minutes to go. Everybody got the 3 graphs? Sharp. Yeah, Diana got it. Good. Anybody else? All the 3? Got it? Yeah. Oh yeah, that Carlo, how do you fix that, right? How do you fix the R square equal to 1, right? So Do you know how to fix that, Carlo? It's not going to be one, definitely. It just happens that your R squared doesn't have enough decimal places there, okay? But we can fix that. Let us fix that. Note, see here my graph, right? My graph, let me zoom in. So you can see my graph has a R squared with 0.9999, right? 4 decimal places. Most likely your R squared doesn't have enough decimal places in there. How many decimal places do you have there, Carlo, for your R squared? I wonder if, well, either way, let me give you the solution here, right? To your problem, right? So that applies not just to Carlo, but to everybody else. If you're getting an R squared equal to 1, we can fix it rather easily. What you have to do, you have to click here in this equation and R squared. You right click it and format trend line label. Okay, format trend line label. And then when you get format trend line label, make sure you choose number and choose as many decimal places as you can, okay? Until you start to see a number that's not 1. Do you see here? I'm getting R squared equal to 1 because I had only 2 decimal places, right? But if I increase it, let's say, to 6 decimal places, the number is no longer 1. Okay, Carlo? You have to increase the number of decimal places of your R squared. Of your, not just the R squared, but the trend line label. Okay, and you can do that for every graph. Click, right click, format trend line label, right? And then category, you change to number and put as many decimal places are it is necessary to display a number that's not 1. Let's zoom out. So we plot all 3 graphs. We got the very low percentage difference, right? And now we should start working on the other things. Most of the activity is to plot the graph. From the graph, you obtain everything that you need to see how good the experiment is. Now it's working the units, right? Units here, units here, units there, right? Units here. 1, 2, 3, 4, 5, 6, 7, 8 cells for the units. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Let's put that in the red color. Yeah. Red color for the units. What you have here are results. Gonna put it which color? Orange. Results. Results. V1 plus V2. And this number should be close to this number here. Very close. It's not going to be exactly the same, but it's going to be very close. And here is the equivalent resistance, right? Here is going to be the summation rule. Here's going to be the division rule for the significant figures. Summation rule, division rule for significant figures. What else we can highlight? Okay, all of that are results. All of that are results. And all of that too, right? They're all results as well. Some of them are numeric results, some of them are equation results. There you go. Some rules, sure. So let's get that here. Let's see how we're gonna do that. Let me make an example here. V total, right? Oh, I'm summing V1 with V2. To get the significant digits for the sum, first you have to know the significant digits of V1 and V2, okay? Okay, Susan? So let's go get the significant digits for V1 and V2. So it's around 6.198, right? Going back here to my table, V, right, is the voltage. Here's the current. It's not the voltage. The voltage is this table here, the third table, right? 1, 2, 3. That's the table. It's going to be 6.1, right? 6.1 is in between those two values. So we get significant figures for significant figures. Okay, Susan? So let's display for significant figures here. Format cell, number, 3 decimal places. Here you go. For significant figures. Here is 4, right? 3.8. 3.8, yeah, is the same number of significant figures as the other one, right? Okay, so 3 decimal places as well. Format. Here you go. 3 decimal places as well. 4 significant digits, 3 decimal places. Now you gotta do the summation, right? The way you do the summation, this one is easy. This one is easy because it has the same number of decimal places. Okay, Susan, this one is easy because it has the same number of decimal places. If you didn't have this same number of decimal places, then it would be a little bit more difficult. So let me number 2, 3. They all have 3 decimal places. 6.198, right? 3.845, right? So the last decimal place is the last significant digit of both measurements. Okay, so you go ahead, you sum them up. When you have this summation, you stop at the very last decimal place. So initially we had 4 significant digits here and 4 significant digits here, right? 3 decimal places with significant digits. So the result must also have 3 decimal places as significant digits. But notice what happened. Initially, you had 4 significant digits for the 2 measurements, but now you're getting 5 significant digits for your result. Okay, which is okay. That's the advantage of summing, make a summation of measurements. Okay, you may increase the number of significant digits. That's for the summation. That's an example for the summation. Okay. Now let's see here. This one here is 29, right? What about this one? No. Let's see. Yeah. Now do you want an example? Oh, here you go. I'm going to display it here. 3 decimal places, 5 significant digits. Number 1, 2, 3. Okay. 3 decimal places, 5. So to get the number of significant digits for this result, you have to know the correct number of significant digits for those 2 results, for those 2 measurements. Okay. And what about for this one? What about for this one? Division, right? Is V total divided by I. We have 7 more minutes to go, right? We have to know the significant digits of those 2. This one is 10.004. Let's see. 10. Okay. 5 significant digits for the voltage. So we have to have 3 decimal places again. Format, number, 1, 2, 3. Okay. And we gotta look at this one here now. That's half milliamp, 0005. Okay. 005, we go. So go in the table for the current. 0, half milliamp. Oh, okay, is that the one? No. Half milliamp, let's see. Should be here. Yeah, should be this one here. Okay. That's 2/10 of a milliamp. That's 9/10 of a milliamp. So it should be 4 significant figures. 4 significant figures. Let's you can either do here, you can either do numeric or you can do scientific. It's better that we do scientific, okay? In this case, we must have 4 significant digits. Consequently, we must have 3 decimal places. Why is that? Okay, here you go. 2, 3. Okay. 4 significant digits, 3 decimal places. 3 decimal places in scientific format. Because this number is very small, it's recommended that you display it in scientific format. Okay, now we know we can proceed to find out what's the number of significant figures for this division here. We have 4 significant figures here. We have 5 significant digits here. So we choose the least. We choose 4. For multiplication and division, we choose the least number of significant digits. For summation and subtraction, we choose the least number of decimal places. Okay? Remember this rule. Significant digits. Significant digits. For summation, for operation, right? For results. Okay. Summation and subtraction. the result must have the least number of decimal places. Multiplication and division. Division. The result must have the least number of significant digits. Okay. 3 more minutes to go. Okay, what else do you need to do? Okay, let's schedule this lab due for May 6th. Lab 5 due May 6th. So units, units, sig figs. What else? Here you go, percentage difference, right? Three graphs. Percentage difference, last table. The percentage difference in the last table. Last table. Units, sig figs. Did I number the tables? No, I didn't number the tables. But should be second, third, and fourth table.
Professor, I have one question.
Yeah, go ahead.
You know how you made the lab 4 due on May 4th? Isn't it going to be a little bit conflicting for it to be due on May 6th, or?
Conflicting for what?
You said lab 4 was due on the 4th, correct?
Yes, that's right, Monday.
And then you said lab 5 will be due on May 6th?
Yeah, 2 days more, right?
Yeah.
Yeah, that's let's see how it goes. If you need more time,
Okay, thank you.
I'll give you. Sig figs, tables 2, 3, and 4, right? Which is into the CL. Okay, so it's 12:50 right now. I have office hours. If you want to hang around, I'll be here. Otherwise, I'll see you on Monday.
Thank you.
Then. Let me stop here. Sherry, have a nice day. Thank you. Let's see. Stop recording.